Okay, you guys ready for part 2? So we're making a transmitter to match our steampunk regen receiver. And the transmitter's got to be battery powered and portable. So we're going to be putting it into this case. The topology of the transmitter is the Jones Push-Pull. Now this Jones Push-Pull is something I built several years ago. It uses a 6N7 dual triode with an indirectly heated cathode. This is going to be new because we're using type 30 tubes, which are directly heated battery tubes. Hopefully the Jones will work. Let's hog some metal and let's get a chassis started and a front panel. Welcome to part 2. This is the antique 1930s style portable transmitter. I raided my friend's junk box and he gave me a pretty beat up piece of aluminum. This chassis seen a lot of work, and it was way too long to work, as the chassis for inside here. So I used my tin snips and chopped off the extra, about that much extra to get it to fit in. And, did kind of the bending on the bench stuff, nothing shop-like or professional, that's for sure. It looks like this is going to go together, right? And I've built a chassis that now can fit inside. He also gave me a piece of panel material which can be cut. Wow, really, Mike? A hacksaw and tin snips? But for a lot of shacks, that's what we're talking about. That's what's in the shack. Not everybody has a machinist buddy. This meter has a certain sensitivity as a microammeter. When you add a resistor in series with it, this internal resistor, it now becomes a voltmeter. If I want to use that meter as both a voltmeter and an ammeter, the first thing I have to do is remove that internal resistor, and it turns back into a sensitive microammeter. So if this meter has a sensitivity of 1000 ohms per volt, how many ohms would we need to make it into a 300 volt meter? That's right, 300,000 ohms, or something like 300,000 ohms. You have the actual resistance of the meter to consider too, but if you ignore that, this resistor should be something around 300K. This is the resistor that I took out of the meter. Let's see if I can read it. Oh, they've got this plastic on it. Let me remove it from the plastic. Some tubing. I don't know if you can see that or not, but that says 300K. So we know we have a meter that we can use as a voltmeter. If we put 300K, we're going to get a 0 to 300 meter. If we do a 30K, it'll be a 0 to 30 volt meter. And as far as the ammeter goes, we'll be using a shunt to turn it into a milliammeter. And I'd like to have 0 to 30 mils be about right for our oscillator transmitter that we're building. And again, 1 meter is going to be for filament voltage, which is very important. And the other is going to be for the plate current and the plate voltage, which is the high voltage from the dry cells. We'll have to do a complete panel layout before we actually have to drill the meter into the front panel. You can take a drill, draw a circle, and take a little drill and drill 1,000,000 holes and then cut out the basic holes and then use a rounded file to smooth it out. Thousands of projects have been done like that to mount these meters. But if you have a way to punch the meter hole, the 2-inch meter hole, or you have some type of a saw that can go in and make the hole, that's going to make it so much easier. And it turns out that in my toolbox I actually have one of those. Now this tool is probably more suited to cutting wood, but on aluminum with a little bit of oil, this is going to work just fine to make some nice 2-inch holes in this fairly thin aluminum sheet metal. So before you actually go to the drawing board and try to come up with a stencil, drill out the front panel, or you go to the straight edge or the square and try to mark the front panel, you need to do a little dull test. Put your components and your knobs and the things you think you're going to have in this transmitter down on the front panel and try to do a layout that fits the parts so that they look decent, they look like the period that you're trying to match, and in our case we're trying to match the mid-1930s. Now by the mid-1930s most modern electronic parts were developed. You know, the toggle switch, the rotary switch, all of these were now standard fare in the 1930s. So let's go through some of the parts. First we have the 2 meters. The one on the left is the voltmeter for the filament of the tube, the 2 tubes. And I have a rheostat here that adjusts the filament off the battery, as well as an on-off switch. All you need to do is kill the filament voltage and the set is off. In the middle we have the tuning indicator, and I've got a couple different styles of lamps shown here. One is just a simple lamp that would show through the panel, and the other is a jewel type holder. We'll see which one I decide to go with. Then we have the combination plate voltmeter and ammeter over here with a switch that puts it into each of the positions. The upper right hand corner we have the transmit and ground or counterpoise connections, a TR switch, as well as the receiver terminals. These are going to feed the steampunk receiver's antenna input. We have the crystal socket. I've got some terminals here that I don't know what I'm going to do with yet, but I should have some connections to the outside world. Not sure what I'm going to use those for. Tuning and loading. And finally, the key jack. That's a good start on the front panel. I think that gives me all the functions I want on the steampunk transmitter for the mid-1930s. Now, in a proper 1930s Jones oscillator transmitter, you actually have 2 tuned circuits. The first tuned circuit is the balanced tuned circuit that sets the oscillation. The second tuned circuit is link coupled to the first through this 3-turn link to this 3-turn link. That is the low impedance tap that goes to the second tuned circuit, which has its own capacitor for resonating. This allows the transmitter to feed a half-wave long wire or high impedance antenna. The idea of having coax was not really there yet, and usually people were using long wire antennas in portable stations. A half-wave long wire or a quarter-wave long wire was the norm. Now, if we want to do a quarter-wave long wire, you would tap down this coil to a few turns and bring that out. And I could actually do that, where I could have a high impedance output that'll drive a half-wave and put the switch in the other position, and it's a low impedance output to drive a quarter-wave. I'm not sure if I want to go to that level of complexity with the transmitter, but you can certainly do it. The other function of having the onboard antenna tuner, and that's what this is. This second coil is the antenna tuner, is it greatly reduces the problem with harmonics. Having a second link coupled tuned circuit on board the transmitter guarantees that you're not going to have a powerful second harmonic. Just simply using this link into a long wire antenna could produce a harmonic situation. If you were to bring this out into coax and a tuned dipole, you'd have much less possibility of any second harmonic energy. But if you're bringing it out to a fan dipole or a trap dipole, you may need extra filtering against the second or third harmonics. So it was very clever how Jones used the dual tuned circuit idea. Having an onboard antenna tuner is a very old idea, it turns out, especially for portable equipment. Who wants to drag along a separate antenna tuner? So once the chassis is basically drilled out with most of the major holes, you want to put the chassis on the panel. And remember, we have to leave room for the mounting. So you just roughly center this the way that you want the chassis in, and now you can come back and mark where to drill through the front panel. mount your major parts or put some screws through the whole thing to hold it all together, because I do want to make this thing look nice, and the way you do that is by getting some of the major parts mounted in the chassis, put the knobs on, and then see what kind of room you have left over. And then take it apart again and do the final drilling of the meter holes and the other switches and connectors and so on that go on the upper part of the panel. Just doing a last minute front panel check. If I think of anything else, I'll keep drilling holes, but I think I'm ready to start drilling and blasting for the other components on the front panel. Okay, we're starting to come along and just doing a little bit of a check as I drill holes. You can see that the next step is to drill the meter holes. This is a 2-inch, primarily made for wood, but we're going to use a little bit of machine oil with it, and with any luck at all, it will go through the soft aluminum. Okay, not the greatest idea in the world, but I did, in fact, make the holes with this thing. I don't think I'd try to do it again, but yeah, I got 2 holes and the meters fit in the holes, so we're going to call that a victory. Nobody got hurt. It's looking pretty good. The meters dropped right into those crude holes. No fuss. The panel is getting kind of marred and marked up with various corrosion and so on. It'll all be buffed out before I paint it. I'll give it some kind of a scratch surface before I paint it. Just have a few more switches to mount and the front panel will be ready, and I will separate the front panel from the main chassis, work on the circuit, and separately paint the front panel before I mount the parts and put them both together. There are only a few things holding the chassis to the front panel, so I can build up the transmitter and ignore the front panel for now. So before painting, I just gave the panel a good light sanding, then I washed it and used some soap on it, and then a little scratch finish on the outside. It should be ready for painting now. Okay, when you are painting with the wrinkle type paint, it's important to clean the plate really well and then do a scratch finish and no primer. Okay, put this right on the bare metal after you've roughed it up with the sandpaper and gotten that scratch finish. Then I like to give it a coat with the panel in the vertical position. Then I lay it as flat as I can, and then I hit it on the other 3 sides. It's important to spray at different angles with the wrinkle paint, and you don't want it to run either. Okay, so keep it flat at that point. And then I just put it out in the sun like this, and usually it comes out pretty good. It wrinkled up quite nice. There's a couple spots that maybe haven't wrinkled yet, but that's pretty good for a first coat, and I may just stick with that. I'm pretty happy with that. I think that came out pretty good. So the Jones oscillator requires a couple of chokes up front to represent a high impedance across the crystal, and that's where we introduce the bias, at the center tap of the 2 chokes. It's not super critical, but you can use these full-size 2.5 millihenry chokes, 1 millihenry chokes, and so on. But I want to do it in a different way. I want to make my own choke for this particular application. And I'm just going to take a coil form that I found. Looks like it's 3/4 of an inch diameter, and I'm going to try to wind my own center tapped choke. And I'm just going to do that by scramble winding about 100 turns and then forming a center tap, and scramble winding another 100 turns just below it. So let's see if my simple 200 turn choke, center tap choke, will work for the Jones transmitter. And here we have the completed center tap choke. Let's see if this is going to work in the Jones, and the crystal is happy with this impedance. This is showing just the basic wiring of the transmitter portion, and I'm just doing this portion here, the output coupling in the second tuned circuit that I'll be using. That's going to come later. So the center tapped output tank is here, and that's this coil here. The secondary tank, which isn't shown in the schematic, and that has its own tuning capacitor. So we have the butterfly capacitor across the center tap coil. You can use a regular capacitor there. You don't have to use a butterfly, but I had one, so I'm using it for better balance. So I don't know if everybody saw this, but there was a mistake. There was a double grounding occurring here. So we have to break up this connection right here. The problem is we are supposed to ground the two directly heated filaments through the key. That's how we turn the oscillator on and off. We're keying the oscillator. That's the ground. Now, I had this drawn so that it was a common ground going between the supplies, and that's a short circuit, and the oscillator would effectively be on all the time. So we have to break this up here. You want to do some basic buzz out, and I left the gimmick caps off to begin with. I have them all made up. They're ready to go to be installed, okay? But I'm not going to install them quite yet. Let's see if the thing oscillates without the gimmick capacitors that encourage oscillation by increasing the capacity between plate and grid. So this is in effect a tune plate, tune grid push-pull oscillator. That's its formal name. So I'm going to tickle this with 3 volts, and I'll probably put something like a 10 ohm resistor in series with it just for safety. And I'll use this power supply back here, my regular bench supply, to supply the 3 volts. We know this is going to be battery powered in the real thing. For the 90 volts, I have a high voltage power supply that I can put a variac on, and I can vary that, from 0 up to whatever voltage I want to run. Type 30s can take fairly high voltage in the CW position. We could even try a couple hundred volts and see what happens. Now, basic buzz out, you definitely want to buzz things out before you apply power. You'll notice that we have a center tap choke here, so you want to go between pin 3 and the other pin 3, and you should have the resistance of the choke. And the resistance of the choke is around 20 or 30 ohms. That's because I used very, very fine wire to make the choke. So that's kind of helpful. It also tells you if you have a good center tap, because you can measure resistance. And that tells you that if you've got 10 ohms on one side, but a short circuit on the other, you've got a problem. Or if you have 10 ohms on one side and 15 ohms on the other, obviously you didn't count the turns properly. But I did measure them, and it's coming out very nicely. It's about 10 ohms on each side of the center tap. So just go around and buzz things out. Make sure everything is connected before applying power. I have everything hooked up, and I've got a piece of coax that goes out to a PL259 connector. That's just on the output link. Right here, it's a direct connection to the link. To ground, there is no loading control. Let's quickly measure the filament input resistance. And I am reading 5.3 ohms. 5.3 ohms for the combined resistance of 2 type 30 tubes. I would expect that to increase if I remove one of them. There we are at 10.2 ohms. Okay, so we know we have good filaments on these tubes. Next thing I'm going to do is hook up the DC supply to light up the filaments of the tube. We'll see what kind of current we're drawing. We need 60 milliamps per tube, so 120 milliamps will be our target current. Okay, let's slowly bring up the power supply. Okay, we're just about there. Okay. We've got our 120 milliamps, so we should have about 2.5 volts on the tube side, even though we're showing more like 3 or 4 volts on the power supply, that dropping resistor, the 10 ohm. And our target's 2.5 volts on the tubes. There it is, 2.521. Yep. So when we put 60 milliamps per tube, or 120 milliamps total, to light the tubes, we get 2.5 volts dropped. That is correct. 100 microhenries of inductance is simply not enough for the crystal. So that's going to have to be rewound. The oscillator came up with a pair of 2.5 millihenry chokes as described. Also, it didn't like the 5.6K resistor I had as a bias resistor. It wanted to go right to ground. But I can report the circuit does work with directly heated triodes. So it will work with the type 19 dual triode, or as we're doing here with a pair of 30s, or a pair of 01As, or a pair of 6J5s, or whatever you have. Now, there were a couple other errors in the schematic, and there's an even bigger mistake. And this mistake is not well described by Jones. And that is, I could not get this to oscillate under any circumstances where I had the rotor of the capacitor grounded. So this schematic was really wrong. I had the capacitor grounded because that's the style of the cap. It naturally grounds the butterfly part of the cap, as you can see. So I said, oh, I'll just ground that. Well, it did not like that at all. I had to literally put a capacitor across the whole thing. So I left the bypass cap, and the B plus feeds the center tap, no problem. I left that center tap and the bypass cap. But I had to put a conventional capacitor across the whole thing before it would oscillate properly. That's worth investigating to see what may be wrong there, and not well described in the text. Some people are using butterfly capacitors. The question is, are they sending the center of the butterfly cap or the dual section cap to plus, or are they sending it right to ground? I think if you do put this to ground, you don't want this bypass cap. You want to go right up through a choke, maybe even to the center tap. That's something that we can explore. But there's something going on there where this thing will not oscillate if you both ground the capacitor's rotor and bypass the center tap. It breaks it up enough that you don't get proper feedback. So let's investigate what that might be in the next video. So with the 2.5 millihenry chokes, and I'll give you a peek under the hood in a second, it will oscillate. And I'm just using a trimmer capacitor to tune it temporarily, so I don't have a capacitor installed at this time. I do have one I'm going to be putting in there, but of course that capacitor will have to be insulated from the chassis, so a bushing will have to be put in here. So let's listen to it. Not bad. That's pretty low voltage. Let's take the voltage up to a couple hundred volts. Okay, and let's look on the scope. Looks pretty good. Let's look at the watt meter, see what kind of power we're getting. Again, there's no loading control and no guarantee that we have a match. About 1.5 watts. That's a good sign. If we're getting 1.5 watts out without doing any matching at all, I think this is going to work okay. Now let's take a peek under the hood. So again, I'm very disappointed that my homemade center tap choke did not work, and I had to use these expensive pi wound chokes. I'm using a couple of 1K resistors. I went up in value just for safety. I can probably bring those back down to the 330s that I wanted to use originally, probably get a little more output power. And notice I've got the trimmer capacitor taking the place of the variable that was attached to the knob in front. And I have a couple of gimmick capacitors here. I'm going to remove those and see if it still oscillates in the next video. Anyway, I wanted to show you what it looked like under the hood. There's not much to this circuit. So here we are with the Jones, and I think that Jones came up with a very clever circuit with this oscillator that uses the dual tubes. I think it was avant-garde. I think it was cute. He didn't completely describe how it worked. And the fact that the oscillator is not well described is the first sign that maybe this circuit is a little bit suspect. The way that it operates with the 3 and 4 pi radio frequency chokes, such as the 2 millihenry, 2.5 millihenry, and so on, is a little bit odd in that if you were to synthesize these chokes with a similar ferrite or a hand wound choke that has a self-resonance that actually is above the frequency, so in other words the choke is working like a choke should, pure inductive reactance, that suddenly the oscillator doesn't want to work at all. It seems to count on some of the oddities of the choke for it to operate. It never was described with indirectly heated tubes, and it seems to require tubes that have quite a bit of gain. The other thing is fooling around with the center tap, and the grounded capacitor caused it not to work in my case. I had to use a simple capacitor across the entire coil and ground the center tap through a capacitor. And that's kind of odd. Why didn't you use a balanced capacitor on the output? So again, there's something odd about this oscillator. Now, do I feel that I probably should have selected a more conventional transmitter topology, such as the oscillator followed by a Class C stage? Yeah, I do. I shouldn't have gone with this. I should have gone with a standard 2-tube transmitter. One is the crystal oscillator, and one is the Class C final, like they did with the Bird Expedition transmitters. Stand by for part 3. Let's get this thing into a box.